Hello and welcome to GCSE Quantitative Chemistry. It's the higher tier part of the booklet. In this booklet we have lessons 3, 4 and 5, 6 and 7. So you should only be doing this if you are a higher tier student. Now, as before, the next pages include the knowledge organiser, and as we're higher tier, all the things that say higher tier only, you will also need to know. Okay, and then there is another page for the knowledge organiser. After this, there is the specification, and there's plenty there to self-assess. I highly recommend you use this before the exams in your revision and preparation. So, lesson 3, calculating mass and moles. So our keywords today are mole, relative atomic mass, relative molecular mass, grams, balanced equation. So we're going to highlight those. Okay, so as you can see, the content we're looking at today is all higher tier only, and this describes the content you need to know. So we're going to start by doing the knowledge check. There are 8 questions. I'd like to pause the video whilst you answer those. Let's go through those then. So make sure you're marking in a different coloured pen to the colour you wrote in. Question 1, define compound. A compound is 2 or more atoms chemically bonded together. Give the value of a mole, that's 6.02 times 10 to the 23 atoms. Now if you've put 6 times 10 to the 23, that's fine. Name the subatomic particles found in the nucleus. That would be protons and neutrons. You need both to get the mark. Make sure that you're writing any corrections in this other pen or ticking to indicate that you got it correct. Question 4, give the units for percentage mass. Well, that would be a percentage. Question 5, write the symbol for relative molecular mass. That's a capital M and a lowercase subscript r. Question 6, name the subatomic particles used to calculate atomic mass. Well, that is again protons and neutrons. Question 7, give the units used to measure mass. That would be grams or lowercase g. Question 8, write the symbol for relative atomic mass. Well, that's a capital A with a lowercase and subscript letter r. So give yourself a mark out of 8 for that, please. And then we're going to move on. So this page may be familiar as we used this in our first lesson in the foundation tier booklet, but today we're overview of our lesson. We're going to explain the meaning of conservation of mass, which we do already know. We're going to be able to balance simple equations, which we should already be able to do, but this is a good review. We're going to define a mole, which again we already know, and we're going to calculate percentage mass, which we had a go at in the foundation tier booklet. Okay, so the relative atomic mass, and you may already have these highlighted because we did this previously. Okay, so the relative atomic mass of an atom is the mass of the nucleus, which is the protons and neutrons. Okay, and it's stated in the periodic table as shown here, highlighted. So it's the top numbers, such as 7 for lithium and 9 for beryllium. And it's not always the top numbers, but it's always the largest of the 2 numbers. Okay, atoms have different relative atomic masses because they have different numbers of protons and neutrons. Okay, MR, relative molecular mass. Okay, so it's not actually described here, so this is relative molecular mass. I'm going to write that down, please. Okay, so you don't have to highlight it if it's going to smear your writing, but if it doesn't, then please do highlight it. So molecules are made from more than one atom chemically combined together. We should know this. A molecule, this is the definition for molecule, more than one atom chemically combined together. Okay. Therefore, to calculate the relative atomic mass of a molecule, we must just add the ARs of each individual atom together. So for example, water, the H2O, so each H is worth 1, O is worth 16, which gives us a total of 18. And we've done this previously. Okay, so the law of conservation of mass, again, we've already done this. We're going to review it again. You do need to know this. Okay, you'll also need to be able to use this and apply it. So the law of conservation of mass states that no atoms are lost or gained or made during a chemical reaction. So therefore, the mass of the products will always equal the mass of the reactant. Okay, so mass of the products equals mass of the reactants, all the other way around. They must be equal to each other. Before must equal after. So sometimes the results of an investigation appear to show a change in mass. Now this isn't correct, it just looks like it changes mass. So if it reduces, it's because gas has escaped to the surroundings or the environment. If the mass increases, it's because a gas may have been added from the surroundings. So if a gas is lost or added to our reaction, then it hasn't been accounted for in our original and final calculations for the product and mass of the products and mass of reactants. So moles, we know that a mole of something is 6.02 times 10 to the power of 23. Because we don't count individual atoms, because they're really small, we must count them in much larger quantities. Those quantities are moles. We can count the number of moles if we know the mass of each atom or molecule, so its mass is its AR, relative atomic mass, or MR, relative molecular mass, and the total mass of the substance in the grams. Okay, so for example, a mole of carbon weighs 12 grams because that's its AR, its relative atomic mass. So 6 grams, that's half that amount, so it's going to be half a mole of carbon. Double it, that's 2 moles, so 24 grams is 2 moles. Okay, so to calculate moles, here we have an equation to help us calculate moles. To calculate mole, you take the mass in grams and divide it by the relative atomic or relative molecular mass. So here we have a table, so your task now is to pause the video and use this equation to calculate that. If you're not sure quite what to do, then that's absolutely fine, and we will go through the first one together now. So the mass here is measured in grams of carbon, so that's 6. We use our periodic table, and our periodic table shows us that the relative atomic mass of carbon is 12. So the number of moles is the mass divided by the relative atomic mass, which is going to be 6 divided by 12, and 6 divided by 12 is 0.5, so there are 0.5 moles there. And you can simply rearrange this equation to calculate any of the missing values, but you need the periodic table to calculate these values. Okay, so we're going to write a little note here saying use periodic table for this. Okay, so to calculate the relative atomic mass or the relative molecular mass, you will need to use your periodic table. And this goes on to the next page. Okay, so continue all the way through and have a go at those. So pause the video whilst you do that. Okay, let's go through those. Once again, when we're marking, we'll need to use a pen in another colour. We've already worked these two out, so if you've got 12 and 0.5, give yourself a tick. The relative atomic mass for hydrogen is 1, and so there are 5 moles, because 5 divided by 1 is 5. Lithium, it was 21 grams, because the relative atomic mass is 7, there are 3 moles, and we can rearrange this so that 7 multiplied by 3 gives us 21. Same here, we use the periodic table to find that the atomic mass, relative atomic mass of potassium is 39. 39 multiplied by 0.5 is 19.5 grams. Okay, moving on to our next page, our next set of results. Okay, so calcium, using the periodic table, has a relative atomic mass of 40. Helium has a relative atomic mass of 4, and 40 divided by 4 gives us 10. Pb, which is the symbol for lead, okay, it has a atomic mass of, relative atomic mass of 207. So 2.07 divided by 207 gives us 0.01, and that's moles. Water, well, we can work out the relative molecular mass of water is 18, as shown in the example earlier on page 6. So 1 plus 1 plus 16 equals 18. So that's 1 each for the hydrogens plus 16 for the oxygen equals 18. And so 32 divided by 18 gives us 1.78. Oh, we've missed one, my apologies. So xenon. 131 is the relative atomic mass of xenon. Okay, and to work out the grams, we would do 131 multiplied by 0.1, giving us 13.1. Okay, so oxygen is O2, so 2 lots of 16 is the relative molecular mass of oxygen, because it's O2. Okay, so this one's going to be 16 plus 16 equals 32. And then 16 divided by 32 gives us 0.5 moles. Okay, so the relative molecular mass of C3H8 is 44. 900 divided by 44 gives us 20.45 moles, or if you've rounded that, 20.5 moles. NaOH has a relative molecular mass of 40, and 40 multiplied by 10 gives us 400 grams. HCl, that's hydrochloric acid, has a relative molecular mass of 36.5, and 36.5 multiplied by 0.01 gives us 0.365, and that's grams. FeOH3, or iron hydroxide, it has a relative molecular mass of 107. 107 multiplied by 2 gives us 214 grams. And lastly, K2SO4, which is potassium sulfate, 174 is its relative molecular mass, multiplied by 5 gives us 870 grams. Okay, so well done. Make sure you give yourself a mark out of 28. Okay, so give yourself a mark out of 28. If you've got more than 20, you've done very, very well there. Okay, because it's easy to make simple mistakes with this. If you've got 10 or less, then you really need to have another go at this activity, okay? Right, moving on. So we've got a checkpoint question here. So, in a fume cupboard, a student heats some calcium nitrate in a test tube. The calcium nitrate decomposes, and this is the equation. Okay, and you can see in front of it here we have 2 of this, and 2 of this, and 4 of this. Okay, so they've already done some balancing. Our relative molecular masses are calcium is 40, and nitrogen is 14, and oxygen is 16. So if you didn't happen to have a periodic table, they've been given to you here. So question A and B. For 1 mark, why is the mass of the solid in the test tube lower after the chemical reaction? Okay, so think about the products there. Why might the mass look or appear to be lower? Okay, so the measured mass is lower. Why is that? Question B. In the reaction, 22.4 grams of calcium oxide is produced. Calculate the mass of calcium nitrate that reacted. And that is worth 5 marks. Okay, so pause the video whilst you do that, please. Okay, so if you're stuck, it's time for a hint. Okay, because I want you to see if you can still work it out. Question A, so it wants to know why the mass is lower after the reaction. So the mass of the solid in the test tube, why is it lower after the reaction? Well, where could that mass have gone? Okay, that's what I want you to think about. Question B, this is a multiple step question. There are 3 stages to this. First of all, you need to work out the relative molecular mass of calcium oxide, CaO. Okay, so work that out. Then, how many moles of calcium oxide, CaO, how many moles were produced? Okay, so it tells us in grams, 22.4 grams is produced, and we know that the MR of calcium oxide is going to be the same amount as 1 mole in grams. Okay, so you could divide the amount produced. So you could divide the 1 mole of calcium oxide by the amount produced to work out how many moles of calcium oxide were produced. And then lastly, to work out the mass of CaNO3, calcium nitrate, that was reacted, you'll need to use the relative molecular mass of calcium nitrate multiplied by the number of moles of CO that was produced, because that's going to be the number of moles that reacted. Okay, so now you have 3 stages for part B as well. Have another go, see how much of that you can get done now that you've had a bit of help. And then we'll go through it completely. So pause the video again if you haven't answered all those questions, or you think you might need to do a bit of changing or checking. Okay, so let's go through that then. So the first question, question A, you need to remember that you have to look at the state symbols. So we know that nitrous oxide and oxygen are gases, and that's shown to us here. Okay, so it says, why is the mass of the solid lower? Well, because some of the mass has left the test tube as oxygen gas and as nitrous oxide gas. So if you've said gases have been released or been lost from the test tube, you get the mark. So 1 mark there. Now, the next question was a real tricky one. Okay, and don't worry if you really struggle with this, because this is hard. So first of all, something I'm hoping you could all do with a bit of help, which was calculate the relative molecular mass of calcium oxide, which was 40 plus 16, which gives us 56. So you get a mark for writing 56. Now you know that 1 mole of calcium oxide is 56 grams. Now you don't get a mark for doing that. However, to calculate the number of moles of calcium oxide produced, we can work out how much is in 1 mole, which is the 56 grams, divided by the amount produced, which was the 22.4, and you get a mark just for writing 56 divided by 22.4. Then that gives us 0.4 moles. Okay, so you get the mark for writing 0.4 there as well. So you could be all the way up to 3 marks here. Okay, then moving on, the mass of calcium nitrate is going to be the relative molecular mass of calcium nitrate, which is 164. Multiplied by the number of moles, which was 0.4, because the number of moles reacting is going to be the same as the number of moles produced. Okay, so 164 multiplied by 0.4, that is worth a mark. Okay, so you get your mark here, and that adds up to a total of 65.6 grams, which gives you your final mark. So that was marks out of 6. Now, if you've got 3 or more out of 6, that is not a bad first attempt at all, okay? If you've managed to get as many as 5 out of 6, that is an excellent attempt. Well done. If you are completely lost with this and you're really struggling, okay, work through this. See if you can work out exactly what we've done, and we'll have another go at something similar again in the future, so don't worry, okay? So we're going to move on to balancing equations. So it's really important that we can balance equations, okay, and the main reason we need to do this is to make sure that the correct amount of atoms or molecules are present at the start of the reaction to ensure that we get the appropriate amount of product. So balancing chemical reactions involves placing large numbers in front of the atoms or molecules so that the quantity of reactants is equal to the quantity of the products. And we've done this before, okay? So putting a 2 in front of the magnesium and a 2 in front of magnesium oxide will balance this equation here. Balancing equations shows a chemist how many moles of each substance are required for the reaction. So it's 2 moles of magnesium to every mole of diatomic oxygen will produce 2 moles of magnesium oxide. So the reaction above requires twice as many moles of magnesium as compared to oxygen to produce the 2 moles of magnesium oxide. So we have a ratio of 2 to 1 to 1. So that will help the chemist know exactly how much of each reactant to put in to get their required amount of product out. Okay, percentage mass. So the percentage mass of an element in a compound is essentially us asking how much of this molecule, this compound, is made up of a particular atom. So for the example of methane, how much of methane is made up of hydrogen? Conversely, you could ask, well, how much of methane is made up of carbon? Okay, so the percentage of hydrogen in methane, well, methane has a relative molecular mass of 16. Hydrogen has a molecular mass of 1. It's not written in there, but it has a molecular mass of 1. Now there are 4 hydrogens in methane, so 4 is what goes into it for the hydrogens, divided by 16, which is the total for the whole compound. So 4 divided by 16 is 25%. So 25% of methane is made up of hydrogen. Okay, now you might think, well, hang on, there's only 5 atoms and 4 of them are hydrogen. How is it 25%? Surely it should be 80%. Well, no, because every carbon atom is considerably larger and considerably heavier because it has a relative atomic mass of 12, whereas the hydrogens are very small and very light, and they have a relative atomic mass of 1. So the 4 hydrogens with their total mass of 4 are 25% of the total of 16. So I'd like you to watch this clip on YouTube. And you'll need to, if you've got a digital copy, you can click on the link or you can type this in. Okay, so pause the video whilst you do that and then come back and we'll do some calculating percentage mass. So we're going to be calculating some percentage mass now, and the idea here is we're going to complete the missing spaces using the following equation. Well, unfortunately the equation's not quite perfect. So percentage mass is equal to the total AR of the element in the compound divided by the MR of the compound times 100, which gives you a percentage. Okay, so let's do the amount of hydrogen in water, H2O, and we'll do that together. So we'll need your periodic tables for this. So the total AR of hydrogen in H2O, well, there are 2 hydrogen molecules, and we need to multiply that by the AR of hydrogen, which is 1. So 2 times 1 is 2. Now the total MR of hydrogen is going to be the hydrogen, which is 2, added to the single oxygen using our periodic table is 16. 2 plus 16 equals 18. Okay, so our AR of hydrogen, our relative atomic mass of hydrogen, and the relative molecular mass of water. Now to calculate this, it is going to be 2 divided by 18, all multiplied by 100, and that gives us 11.1 recurring, but 11.1%. Okay, so remember, if there is a very large number of decimal places, if you could round it to 1 decimal place, that would be wonderful. Okay, so you've seen how this works, the method. You don't have to write out your workings, but I highly recommend it because it'll help you figure out where you went wrong if you make a mistake. You also don't have to write them out here. When I did these and typed all the answers up, I used like 3 pages of A4 paper, scribbling out all my calculations. And once again, as this is science, you are always allowed to use a calculator, and please do so, because as you can see, the percentages are going to be quite hard work. Okay, but don't forget you will need to round them appropriately. So pause the video whilst you do that. So let's go through those. Make sure you've got a pen in a different colour to mark with. So as we've already gone through these ones, so it's 2, 18 and 11.1% for hydrogen. Okay, carbon, it was 12, 16 and 75%. Hydrogen has been done for us. Magnesium oxide, 24, then 40, then 60%. Zinc chloride, it was 71, 136 and 52.2. The nitrogen in nitric acid, 14, 63 and 22.2%. Carbon in carbon dioxide was 12, then 44 and 27.3%. So this activity continues on to the next page. So if you haven't already done these, please continue to work through them. Okay, if you're not sure or you've made a lot of mistakes previously, have a look at how these have been worked out, review the video as to how the calculations have been done, and try to follow that method. If you get stuck, please do email the teacher. So pause the video if you need to and continue with those, and then we'll go through them together. Okay, so the carbon in C3H8 it was 36, 44 and 81.8%. Hydrogen in NaOH, sodium hydroxide, was 1, then 40, then 2.5%. The chlorine in hydrochloric acid, 35.5, 36.5 and 97.3%. The hydrogen in iron hydroxide, FeOH3, was 3, 107 and 2.8%. The sulfur in potassium sulfate is 32, 174 and 18.4%. The oxygen in C6H12O6 was 96, 180 and 53.3%. So give yourself a mark out of 36 for all of those. If you got more than 30, that is exceptionally well done. If you got more than 25, well done. If you've got 10 or less, then you really need to have another go at that, because that demonstrates you've had some real problems. And do please feel free to email your teacher if you are stuck. Okay, so our next learning activity is calculating moles, masses, and percentages. So for each reaction, completing the following tasks, which requires you to fill in the white boxes, as you'll be able to see, it's just like these. So these are the white boxes it's talking about. It wants you to fill in, and that goes all the way up to page 9. So there are 3 you need to complete, and there's one example as well. So first of all, you need to balance the chemical equation. Then you need to state how many moles of each substance there are in the reaction. So balance it. How many moles are there? Then write the either relative atomic mass or MR of each substance, and you'll need to use your periodic table to do that. Okay, then you need to calculate the MR of the reactants and the products, which is the relative molecular mass multiplied by the number of moles. Then, using the law of conservation of mass, calculate the missing mass. Lastly, or second to last, calculate the actual number of moles that have been reacted or produced, which is mass divided by relative molecular mass, and then calculate the percentage mass of the element, which is the mass of the element divided by the mass of the molecule. Now, let's go through that as a worked example. So first of all, balance it. Part A is balance. So it's given us the following equation. Magnesium plus oxygen turns into magnesium oxide. So let's draw ourselves a nice red line separating the before and after. Okay, so we have reactants and we have products. Now you don't need to do this if you don't want to. Okay, so we have on this side we've got 1 magnesium, and on this side we have 1 magnesium, so that's good. However, we have 2 oxygens here and only 1 oxygen here. So we will need to put a 2 on this side, which they have done here. Then we have 2 magnesiums, but only 1 on this side, so they've also put a 2 here. We should check our work when we've done that. So 2 magnesiums on the reactants and 2 magnesium atoms in the products. 2 oxygen atoms in the reactants and 2 oxygen atoms in the products. Good, it's balanced. Now, how many moles are there? Well, this one is really easy. What number did you write in front of your balanced equation? So 2, so it's the same number. We didn't write a number, so that's just 1 and 2. So that's real simple, that one. Using our periodic table, the relative molecular mass of magnesium is 24, and they've written that here. Oxygen is 16, and they've written that here. Magnesium oxide, need to add 24 to 16, which gives us 40. Now we need to do some multiplication. Okay, so this is part D, which is the relative molecular mass, which is what's in here, so that's 24, multiplied by the number of moles, which is 2, which equals 48. This is going to be right, so this one's tricky. So oxygen is 16, but there are 2 oxygens here, so it's diatomic oxygen atoms. So it's going to be 16 plus 16, and that gives us 32, and there's only 1 of those. And you'll have to do that if you ever see a 2 afterwards, okay, like a subscript 2. Now here we have magnesium and oxygen, which is 40 multiplied by 2, so 2 times 40 equals 80. So we have our answers here. Next stage, stage E. So calculating the missing mass, okay, so it's going to be the how much have we been produced. Now we've got all of them here in this one, but in your further examples, you won't have that. So here we have, for example, 460 grams and 710 grams before, and then using the law of conservation of mass, you can add those together to get the products, to get the reactants. So the products must always be equal to the reactants. Okay, and the same goes for this one. So your products must be equal to your reactants. So you add these together, whatever that total is, you take this number from it and that gives you your answer. So that is just basic maths. So lastly, F is the mass divided by the relative molecular mass. So it's E divided by C. And so for magnesium, that's going to be the 48 divided by the 24 to give us 2. Now, oxygen is a diatomic molecule, it's a bit more complex than that, so it would normally be divided by C, but because there's 2 oxygens in our diatomic oxygen, it's going to be 2 lots of 16, so it's actually going to be 32 divided by 32 to give us 1. This is a common source of errors. And lastly, 80 divided by the 40, which gives us 2. So we have our ratios here of 2 to 1 to 2. Okay. So, calculate the percentage mass of oxygen in MgO. Well, the relative molecular mass of oxygen is 32. The total relative molecular mass of MgO is 80. So it's 32 divided by 80, all multiplied by 100, gives us 40%. And that's what we need to do for each of them. So I'd like to pause the video whilst you go through each of the following sets of tables, complete those, and then we'll go through them. Okay, so let's go through those. Make sure you have a pen in a different colour to the one you wrote in, so it's very clear what's your own work and what's corrections. Okay, let's go through the first one. So to balance it, you need to put a 2 in front of the sodium and a 2 in front of sodium chloride. So there were 2 moles of sodium, 1 mole of chlorine, diatomic chlorine, don't forget that, and 2 moles of sodium chloride. So our relative atomic mass of sodium is 23. Chlorine is 31.5 and sodium chloride is 58.3. Okay, so 23 multiplied by 2 is 46, 35.5 multiplied by 2, because this is diatomic, okay, is 71, and 58.5 times 2 is 117. The missing mass, you need to add these two together to give you 1170 grams or 1.17 kilograms. So to calculate F, the number of moles that were actually produced or reacted, we do the mass, 460, divided by the relative atomic mass of 23 to give us 20. 710 grams divided by the 71, which is the relative atomic mass of diatomic chlorine. Remember, there are 2 of them, so you must do twice the number, which gives us 10. And then for sodium chloride, it is the 1170 grams divided by 58.5, and that gives us 20 moles. Okay, so to calculate the percentage mass of chlorine and sodium chloride, the method you were shown to use was 71, which is the amount of chlorine, which is here, divided by 117 here, all multiplied by 100 gives us 60.7%, or if you've rounded it to 61, that's fine. An alternative method, which doesn't always work well, but does work well for this one, and you could have the marks if you've done it this way, is 35.5, the relative atomic mass of chlorine, divided by 58.5, the relative atomic mass of sodium chloride, multiplied by 100, also gives you 60.7. So either one of those methods is fine. Okay, so make sure you put in any corrections that you need to and that you followed this. And then we're going to move on to the next one, number 3, the reaction between methane and oxygen forming carbon dioxide and water. So to balance, you need to put a 2 in front of oxygen and a 2 in front of water. So there's 1 mole of CH4, methane, 2 moles of oxygen, 1 mole of carbon dioxide and 2 moles of water. The relative atomic mass of methane is 16, 32 for oxygen, 44 for carbon dioxide and 18 for water. Multiplying the relative atomic or molecular mass by the number of moles is 16 for methane, 64 for oxygen, because though it's 32 for diatomic oxygen, there are 2 moles that make 64, and 36 for water. Using the law of conservation of mass to calculate 640 grams. So you add these together, take away 160, that leaves you 640. And our mass divided by our relative molecular mass calculates for us the actual number of moles produced or reacted. So 10 moles of methane, 20 moles of oxygen, 10 moles of carbon dioxide, and 20 moles of water. Now calculate the percentage mass of oxygen in H2O. Well, oxygen's here, and it has a relative molecular mass of 32, divided by 36, which is the relative molecular mass of oxygen, multiplied by 100 gives us 88.9 or 89% if you've rounded up. Okay, so moving on to number 4. Sulfuric acid, H2SO4, reacts with potassium hydroxide to form potassium sulfate and water. To balance the equation, you need to put 2 in front of the potassium hydroxide and 2 in front of water. So therefore it's 1, 2, 1 and 2 moles. The relative atomic masses are 98, 56, 174 and 18. Multiplying the relative atomic or molecular mass by the number of moles gives us 98, 112, 174 and 36. Calculating the missing mass using the law of conservation of mass gives us 17.4 grams, which we should put a G in there, wonderful. So taking the mass and dividing it by the relative molecular mass gives us 0.1 moles, 0.2, 0.1 and 0.2 moles. To calculate the percentage mass of sulfur in H2SO4, we take the relative molecular mass of sulfur, which is 32, divide it by the mass of the relative molecular mass of H2SO4, sulfuric acid, which is 98, multiply it by 100, we get 32.7%, or 33 if you've done it just to the nearest whole percent. Question 5. The reaction between nitric acid and copper oxide forms copper sulfate and water. So to balance it, you put a 2 in front of the nitric acid and make sure you've filled in water here. Okay, so there's 2 moles, 1, 1 and 1 mole. The relative atomic mass, or molecular mass in fact, of HNO3 nitric acid is 63, 79.5 for copper oxide, 187.5 for copper sulfate and 18 for water. Multiplying this relative atomic or molecular mass by the number of moles gives us 126, 79.5, 187.5 and 18. So we didn't do this one the same way with using the law of conservation of mass, because we didn't have one full side of the equation, so we had to do this one slightly differently. Now, remembering what we've done previously, we know that there are 2 moles of HNO3 and the relative molecular mass of HNO3 is 63. So we know exactly how much 2 moles of that is going to be. It's going to be 126 grams. And we can do this with each of these. So if we do it for the one where we have the missing mass of 3.6, okay, so we take our number of moles, which is 1, multiply it by the relative molecular mass, which is 18, which means that for 1 mole of this, it would be 18 grams. Now we have 3.6 grams. So to work out how many moles there are, we can divide those two. So 3.6 grams divided by 18 gives us 0.2. Let's just show that on screen. Okay, so that tells us that we have produced 0.2 moles of water. Okay, so we've had to calculate how much water we've produced. So we know that the ratio here is 2 to 1 to 1 to 1. Okay, so our ratio is 2 to 1 to 1 to 1. So that tells us that we're producing 0.2 moles of copper sulfate, 0.2 moles of copper oxide, and because this one ratio is 2, we multiply that by 2 to give us 0.4 moles of nitric acid. Now, because we've worked out F a different way, okay, the amount that was produced, we can now work backwards from that position to calculate the amount of mass that's there or was produced. So this time what we have to do is multiply our D, which is our relative molecular mass of the reactants here, or of the products here. So 187.5 multiply it by 0.2, and that gives us 37.5. So we're going to write this in. I'm going to use a pen here because it's much finer. So 187.5 multiplied by 0.2 will give us 37.5. Okay, so it's D multiplied by F. Okay, so another way of doing this is D multiplied by F. Okay, so we'll do that for all the rest of them as well. So 79.5 multiplied by 0.2 will give us 15.9. And 126 multiplied by 0.4 will give us 25.2. Now don't worry if you didn't manage to achieve this. This is the height of trickiness, okay? And if you haven't managed this, that's absolutely fine. Don't panic, don't worry about it. You'll get more familiar with this as time goes on as we work through the booklet. So lastly, calculate the percentage mass of oxygen in the copper sulfate. So oxygen has a relative atomic mass of 96, because obviously oxygen doesn't actually have a relative atomic mass of 96, it's got 16. Okay, but there are 3 oxygens inside the bracket multiplied by the outer 2, so 3 by 2 is 6, so 6 lots of 16 equals 96. Okay, and so that's where this number has come from for the mass of oxygen. So we had to calculate the amount of oxygen in the entirety of copper sulfate. Now the total relative atomic mass for copper sulfate is 187.5, so 96 divided by 187.5 multiplied by 100 gives us 51.2%, or 51% if you've done it to 1 decimal place. Okay, well done. That was very tricky, and don't panic if you haven't managed to do them all, especially this last part E. That was probably one of the trickier bits to do. Okay, so we're going to move on now, and we are going to do the knowledge and application check on page 11, and moving on to page 12. There are 13 questions. Now there isn't a lot of room for questions 9 through 13, so feel free to use the rest of the page or the student notes page. So pause the video whilst you do that, and then we'll go through that together. So let's go through those questions. Question 1, name the smallest subatomic particle, that is the electron. Please make sure you're marking in a pen of a different colour and you're adding corrections as you go, or ticking to indicate you're correct. Question 2, where is the mass of an atom located? Well, it's located in the nucleus. Name the 2 subatomic particles that make up the mass of an atom, that's protons and neutrons. Define the law of conservation of mass. Well, the mass of the reactants equals the mass of the products. Always. Question 5. State where the numbers are placed when balancing equations. So before the chemical formula or in front of them. Define MR. Well, that is the relative molecular mass. You can add up the atomic mass, relative atomic mass, of all the atoms in the compound. Give the units for measuring mass. Well, that's grams or lowercase g. State the value of a mole, that's 6.02 times 10 to the 23 atoms. Although it doesn't have to be atoms, you can have a mole of anything. Okay, next question 9. Calculate the relative atomic mass of sodium hydroxide, NaOH. So, the relative atomic mass of sodium is 23, oxygen is 16, and hydrogen is 1, giving a relative molecular mass for sodium hydroxide of 40. Calculate the percentage mass of sodium in sodium hydroxide. So sodium is 23, we'll divide it by 40, which is the total total molecular mass of sodium hydroxide, multiply it by 100, and we get 57.5%, or 58% if you've rounded up. Question 11. Calculate the percentage mass of hydrogen in the magnesium hydroxide. So there are 2 hydrogen atoms in magnesium hydroxide, both have a relative atomic mass of 1, giving us a total atomic mass of 2 for hydrogen, divided by 58, which is the relative molecular mass of magnesium hydroxide, all multiplied by 100 gives us 3.4%. Question 12. Calculate the percentage mass of carbon in ethene. Well, there are 2 carbon atoms in ethene, both worth 12, giving us 24, divided by 28, which is the relative molecular mass of ethene, all multiplied by 100, which is 85.7%, or 86% if you've rounded to the nearest whole number. Question 13. Calculate the percentage mass of hydrogen in sulfuric acid. So there are 2 hydrogens, giving us 2 times 1, which is 2 for the relative atomic mass of hydrogen, divided by 98, the relative molecular mass for sulfuric acid, all multiplied by 100 gives us 2.0%, or just 2% if you've done it to the nearest whole number. So give yourself a mark out of 13 for that. If you've got 10 or more correct, that's very well done. Excellent. If you've got 6 or less, then you really need to have another look through this lesson and review the content before moving on. That's the end of our lesson. Thank you very much.